thanks everybody for coming, and especially on a non-usual meeting time for the CHAMP seminar. I'm very happy to introduce Ayah Almousa, who will tell us about polarizations of irrelevant maximal ideal to the D.
Thank you very much. Thanks to the organizers for inviting me. I'm very happy to be able to speak and to be able to share my research with you all. So, sorry, I'm having this unnerving echo from my own tablet of my voice. So I'm just going to turn the volume up. Well, okay, it's fine. Okay, so this is all joint work with Gunnar Fløystad and Henning Lohne, who are both at University of Bergen in Norway. So let's just jump right in. So what? Oh, of course, my pen is not working. It was working when I tested it before. And now it's okay. Here we go. All right. So what is a polarization? For those of you that may be familiar with this idea. So here's the idea, is you start with an ideal, and it's a monomial ideal in some polynomial ring, right? And we'll just over any field and variables. And what we're going to do is we're going to polarize it to some square-free monomial ideal in some bigger polynomial ring S tilde. So now it'll have more variables. And in the process of polarizing, we're going to, my pen just stopped working. And in the process of polarizing, we're going to be preserving all of any homological invariant that you might care about. Homological properties. Okay, so why would one do this? So there are sort of a few reasons that this has come up over the years. So sort of the most common way that you'll see a polarization used is because we know that square-free monomial ideals are in one-to-one correspondence with simplicial complexes. Right? We know this from Stanley-Reisner theory. And so often, if you're studying a monomial ideal, it's nice to be able to polarize it. You get a square-free monomial ideal, and now you get to use all of these sort of techniques from topological combinatorics to gain information about the ideal. And then you can depolarize, or just from knowing that all of the invariants are the same, then you get the information that you wanted about the ideal that you started with. So this is sort of the most common reason that you'll see it used. It also, sort of one of the first places that a polarization was used, it was in Hartshorne's 1966 paper about connectedness of the Hilbert scheme. And actually, he didn't call them polarizations. He was using distractions, is what they're called, which are really a specialization of a polarization. And then recently, this was also used by Nagel and Reiner. And this was around, so the paper was published in 2009, but I think they wrote it in 2007. What they do is they use a non-standard polarization to build a minimal cellular resolution of strongly stable ideals. So what they do there actually is you start with a strongly stable ideal. I'm not going to define it. I'll just say that they're ideals with really nice combinatorial properties. One key thing is that powers of the maximal ideal are in here. And then they polarize using a non-standard polarization. And then they build a cellular resolution of the polarization and then from there they depolarize, and it turns out that the same cellular resolution works. Same resolution works for the ideal that you started with. So, okay, and yeah, so I'm gonna touch on all of these applications at various points, especially if you're interested in connectedness of the Hilbert scheme or applications to the structure of the Hilbert scheme, you should definitely stay until the end. But let's formally define what a polarization is. So formally, well, okay, and one thing I should add is, in spite of all of these places that polarizations have shown up in different ways, there's been no real systematic study of polarizations in and of themselves until now. So let's define a polarization. So let's let I be an ideal in this polynomial ring, x1 to xn. And so we're going to let I be an Artinian monomial ideal. So I'm just going to focus on the Artinian case today. Artinian monomial ideal. And so, okay, let's let di be the highest power of xi that shows up in a generator of I. And I'm going to let this set x check of I be this set of now double indexed variables. So it'll be xi1, xi2, all the way to xi di. And then I'm going to build this new polynomial ring S tilde out of these sets of variables, now double indexed variables that I have. So this is a bigger polynomial ring, xn, in the variables of the x checks. So we say that I tilde of S tilde is a polarization of I if the following is a regular sequence. So sigma is, so I'm going to have x11 minus x12, x11 minus x13, x11 minus x1 d1. And then I'm going to do the same thing for the x2s, x21 minus x22, x21 minus x23, x21 minus x2d2, and so on. So I do this for all of these sets of variables, xn1, xn2, xn1 minus xndn. Is a regular sequence, is a regular S tilde mod I tilde sequence. And if I take I tilde and I tensor with S tilde mod this sequence, it should be isomorphic to the ideal that I started with, right? So we're modding out by a regular sequence. So all of our homological properties are preserved, but we sort of threw in enough variables into the ring so that now it can be square free, right? So the way that I think about this is you're starting with an ideal. So for example, let's say that I have the monomial x1 squared, x2, x3 cubed in my ideal, right? Then the way that I think about it is you sort of take so you take this x1 and you're sort of mapping it to a subset of variables, in this x check of I, where this subset has cardinality, the power of x1, right? So for example, if I were doing the standard polarization, it's going to take x1 squared, x2, x3 cubed. Well, okay, so what I'm going to do is I'm going to take x1, so I'm going to have, and I'm going to sort of count them. So I'm going to have x1, 1, and x1, 2. And then I'm going to start the count over when I go over to x2. So it'll be x2, 1. And then when I go over to x3, I'm going to, again, start the count over x3, 1, x3, 2, x3, 3. But something else that you could do, so this is called, now it's called the box polarization. The reason why it's called this is because this is the polarization that Nagel and Reiner used up here. And this cellular resolution that they built is called complex of boxes. And so this polarization has now been called the box polar. They didn't actually call it that, but now that's what people call it. So the box polarization is gonna instead, so I start with the same monomial and I want to polarize it. Now it starts out looking the same, but now what sort of happens is now I go to x2 and I sort of keep counting, right? So I have 1, 2, so now I have 3. And then with x3 cubed, I have x3, 4, x3, 5, x3, 6, right? So you can see that this number at the end is sort of it's the degree of the monomial, right? So one way to visualize this also comes from the complex of boxes construction, is as follows. So let's visualization. So I'm going to define the following. So delta n of d is going to be the lattice simplex of vectors in n to the n, but I'm going to allow 0 to be a natural number here, and such that the sum of all the entries in the vector is equal to d. And so so you can, if I draw this, okay. So for example, this is, if I'm drawing delta 3, 2, I have 2, 0, 0 up here, 1, 1, 0 here, 1, 0, 1, 0, 2, 0, 2, 0, 0, 0, 2, 0, 1, 1. And so you can see that everything in here is in one-to-one correspondence with, so I'll say every A in delta and D is in one-to-one correspondence with a generator of a power of the maximal ideal. It's 1 to the xn to the d, right? So for example, okay, so I'm going to draw it again. Actually, I'm just going to erase it and do it here. So now I can sort of relabel these if I wanted with, instead of each of the vectors, I have x to the a, right? So now this is x. So now I'm going to say that now my polynomial ring, just so that I don't have to do the double indices, is going to be x, y, z. So then I have x squared, y squared, z squared, xy. xz, yz, right? And so one way that you can view this picture is you can say, you can sort of see each edge in this picture. Each edge symbolizes a linear syzygy, right? So I put an edge in this picture if I have a linear syzygy between two of the generators, right? But so now if we took this picture and we relabeled it and we polarized and then we looked at the linear syzygy graph for the polarization. So I'm going to do the box polarization here. Then it's going to look like this. So now my corners, I'm always just going to be counting up. So it's degree 2, so the x1, x2, y1, y2, z1, z2. And then I'm going to have x1, y2, because I count up, x1, z2, and y1, z2. So you see that actually we do not have a linear syzygy here, right? These two are relatively prime. So this is a quadratic syzygy, right? So, so yeah, it seems like, okay, well now I have this picture, and if I remove an edge, then I get a polarization out of it, right? You can sort of imagine that now if I have this picture, I can go the other way and create a polarization in a nice way, maybe. And if I have a polarization, it gives me this picture. And then if we look at the standard polarization, you'll see that actually no edges are removed. And that's totally fine. Z1, Z2, so this one, you start the count over with every variable, right? So x1, Z1, y1, Z1. So I have all of my linear syzygy edges here. But okay, what if instead I had a what about the following? What if instead when I did my polarization, I ended up with something like this. So I have x1, x2, y1, y2, z1, z2, and on these corners here, I'll label them x1, y1, x1, z1, and y2, z2. So is this a polarization? Well, if we go back to our definition, in order for it to be a polarization, we need that all of these variable differences, like x1 minus x2, y1 minus y2, and z1 minus z2, or we need all of these to be regular elements. But that actually doesn't work here. So if we look at y1, y2, and we multiplied it by x1, z2, this is not an element in my ideal. But then if you rewrite this, you see we have an x1, y1, and then we have y2, z2. Right, so these are both 0 in the ideal, or in S mod I tilde, S tilde mod I tilde. So this is 0. This is not a regular element. So it seems like we can remove one edge from here and it's fine. But when we remove two edges, somehow that's a problem. And so in the 3 variable case, Henning Lohne gave the following theorem. So first I should preface by saying, so we're sort of focusing on, I'm going to draw a bigger picture so it's a little easier to see. So now this is delta 3, 3. So we're sort of focusing on these down triangles. They're the triangles that are pointing down. And in the box polarization, the bottom left one is always removed. But it seems like as long as you are only removing one, it'll still correspond to a valid polarization. And this was shown by Henning Lohne in the 3 variable case. Let me make sure I write this correctly. So for every choice, of removing exactly one edge from each down triangle of delta 3D. So you only did this for 3 variables. There exists a polarization of x, y, z to the d such that the corresponding cell complex supports a minimal cellular resolution of I. I didn't say what I is. Of x, y, z. So one question is, okay, so this works for 3 variables, but how could one generalize this? And also, what framework do we need in order to generalize this? So,
Ayah,
yes.
should that be a minimal cellular resolution of the polarization?
It's of the polarization. Okay, you're right. So of the polarization, but it also gives rise to 1 of x, y, z to the d.
Okay.
Of the polarization. And therefore, so you can depolarize, and then you'll get a minimal cellular resolution of the original idea as well. Okay. So, okay. So how to generalize this? So let's think about delta 4 of d. And so now you can kind of imagine that, okay, what's the generalization of a down triangle? It's sort of a down tetrahedron, only we only care about the one skeleton right now. So it might look something like this, right? And so what is the equivalent of only removing one edge? So it turns out that if you remove multiple edges, it'll still correspond to a polarization. So actually what the idea is that what we want is a spanning tree of this complete graph, of complete down graph. So, you know, so in this case, that would look something like this with these edges removed, or this with these edges removed. But we sort of need a framework in order to translate this idea of like checking a regular sequence to this idea of checking a spanning tree. And so here's sort of the perspective is, so if you look at delta n of d, you can put a partial order. Well, you can put many partial orders. Put partial orders. Where we say that a vector A is less than a vector B. Well, I'll say less than or equal if AI is less than or equal to BI and AJ is greater than or equal to BJ for all I not equal to J. So let's look at this picture again. So 1, 0, 1, 0, 1, 1, 0, 2, 0, 0, 0, 2. So if I consider the partial order 1, or I can also call it x, because I'm just sort of focusing on the x variable, right? So you see that 2, 0, 0 is going to be the largest element in this poset, and everything is going to be, everything else is beneath it, right? We see, for example, 1, 1, 0 and 1, 0, 1 are incomparable. But then if you instead considered greater than or equal to in 2, now it's sort of like you have to imagine that you rotate the triangle, right? So now this one is the max of greater than or equal to 2. And so, for example, you know, we see that 2, 0, 0 is greater than 1, 1, 0, but then on the flip side, 1, 1, 0 is greater in the second index than 2, 0, 0, right? And so now we're going to view polarizations as order-preserving maps in the following way. So again, as a reminder, x check I is this bigger set of variables. And I'm going to let B of x check I be the Boolean poset on the D elements of xi. X check I. And and it turns out that a polarization give order preserving maps from delta n of D to the Boolean poset. So this is sort of what I was saying earlier about how, you know, you take, well, let me draw a bigger picture so that you can sort of see what I mean by this. Okay, I put the graph paper background and I'm not really using it, but it's okay. Okay, so at the top, so let's consider just the partial order with respect to x. So at the top, what is this vector going to be mapped to? Well, we always know that it's going to be x1, x2, x3, whatever the degree is, right? So this is delta 3, 3 that I'm looking at, right? And then anything under it has to be, so now these two are going to be a subset of size 2, because I need two x1s, or I need two x's. So, and they have to be contained in this set. So actually in this case, I can pick any two. I can pick x1, x2, and x1, x3, for example. But I need now that this one in the middle, whatever is in here, because this one is less than both this edge, both this one here and this one here, with respect to the partial order, I need that in the Boolean poset, this, whatever I put here is contained in both of those. So now I have to put x1. And then at the bottom, these are all empty with respect to x because there are no x variables down here. And so the key idea is that we're able to use these maps to translate. Basically, there are a lot of really nice lemmas about these maps that allow us to translate these questions about checking a regular sequence to checking for a spanning tree in each of the down triangles. And so this is the framework. I don't want to get too much into it, but that's sort of the idea. And so using this, we get our theorem. So a set of isotone maps, x1 to xn, determine a polarization of x1, xn to the d. If and only if, so this goes both ways, for every, we call them complete down graph. So this is sort of the generalization of the down triangle. In this lattice simplex picture, the linear syzygy edges contain a spanning tree. Syzygy edges contain a spanning tree. Okay, so now that we have this this sort of visualization and this framework, what can we learn about polarizations from this? So there are a couple of, so I'm going to sort of shift gears and talk a little bit about an application. So I'm going to focus on the Stanley-Reisner complex. Of polarizations of Artinian monomial ideals. So right, we talked earlier, and many of you are probably familiar with this. So given a square free monomial ideal, it corresponds to a simplicial complex, and often we can learn a lot about the simplicial complex. We can learn a lot about the ideal from learning about the simplicial complex. And also on the flip side, like there's a big history of commutative algebra helping combinatorics as well in this way, by gaining information about simplicial complexes from the monomial ideals. And so we want to understand the structure of the Stanley-Reisner complex of these polarizations. And so we have the following theorem that sort of gives a hint as to what the structure might look like. So let delta J be the simplicial complex associated to a polarization, to a polarization of an Artinian monomial ideal. Then every codimension 1 face of delta J is contained in 1 or 2 facets. And so it turns out that there's a theorem of Bjorn that a constructible simplicial complex with this property is a topological Euler sphere. And so it's sort of a question, are these polarizations topological balls? So in the case that they're complete intersections, we think that they're spheres, but I don't want to get super into it. But yeah, sort of a question is, are polarizations topological balls? Well, are there simplicial complexes topological balls?
So maybe the answer is too technical, so I don't want to force you to give me a complete answer, but can you give me an idea of what constructible means?
So I'm going to get into that. I'm not going to define constructible, but I'm going to talk about something that implies constructible.
Okay, that sounds good.
So right, so yeah, so the key thing that we need is constructible. And so one thing that's a little bit easier to talk about is shellable. So yeah, in particular, are they constructible? And so the plan of attack is to check if they're shellable, because shellable implies constructible. Now, I'm also not going to define shellable, but you'll see why soon. I mean, it has a very natural combinatorial definition. It's like you have to be able to order the facets in a nice way that you can build the simplicial complex so that it has nice iterative properties. But here's some facts that I think will clarify things. So if a simplicial complex is shellable, so that implies that the corresponding ideal is sequentially Cohen-Macaulay. But actually, we're dealing with pure shellable. So it just implies Cone-Macaulay. And then over here, so now we can also consider the Alexander duals of these ideals. So the Alexander dual of a simplicial complex basically means that it creates a sphere when you put them together, or like a complete simplex. And let me define the Alexander dual. So I'm just going to put a definition. So if I is a square free monomial ideal, then we say that I dual is the Alexander dual. I should write out the word Alexander. Sorry, sometimes my tablet, my pen just stopped working. Okay, here we go, it's back. This is the Alexander dual. Of I, if the monomials in I dual are precisely those with non-trivial common divisor. With every monomial in I, right? So you just have to check this on the generators typically. And so the Alexander dual is very important, and often you can glean a lot of information about the ideal you started with by instead looking at homological property of the Alexander dual. Sometimes one of them is easier to look at than the other. And so one sort of way to see the relationship between these things is, so if I is Cone-Macaulay and it's a square free monomial ideal, then that happens if and only if the Alexander dual has linear resolution, has linear free resolution. And the simplicial complex being shellable happens if and only if the Alexander dual has linear quotients, which Aldo talked about last week in the Fellowship of the Ring talk. I'm going to define it. I'll define it. So the idea here is that you can order the generators of, okay, so I'll say I has linear quotients. If there exists an ordering of the generators, so F1 to FR, if there are generators, such that if you consecutively take colons, so if I take K of them and then I colon with the next one, it's equal to a complete intersection. You just get an ideal of variables here. And this is very nice. So it's not just a linear resolution. Now you can do iterative mapping cones, and it has a really nice structure. So yeah, so this implies a linear resolution over here. And so actually what we're going to do is, instead of directly checking if the simplicial complex is shellable, we're going to try to understand the Alexander dual of polarizations and then try to show that they have linear quotients. Okay, so it turns out that so it turns out that we found the Alexander dual explicitly for polarizations of powers of the maximal ideal. So I'm not going to give a lot of details. I'm just going to sort of show by example how this works, because the same visualization from this sort of triangle diagram also gives the generators of the Alexander dual. And so let's do an example. So I'll just do the box polarization of x, y, z squared. So x1, x2, y1, y2, z1, z2, x1, y2, x1, z2, z2. And so what I'm going to do is now, before I was focusing on the down triangles, but now I'm actually going to focus on up triangles. And I'm even doing this if an edge is removed. And so the idea is that I'm gonna sort of pull an x variable from the top of the triangle. I'm gonna pull a y from the bottom left. I'm gonna pull a z from the bottom right. And then, and so yeah, this framework with the maps that I had talked about earlier sort of gives us the tools to be able to show this. So now let's do that. And then we're going to pull a variable from each of these corners and we're going to multiply them together. So for example, if I look at the first triangle, I can pull either x1 or x2 from the top. But then from the bottom left, there's only one y I can choose. And then from the bottom right, there's only one z. And then the second triangle, there's only one x I can choose from. And there's also only one z I can choose from. And then we see that I can choose either y1 or y2, but this one is already in here. So I'll just do y2, or sorry, y1. And then for the last triangle, it's the same thing. So I have only one choice for x, I have only one choice for y, and then I have two choices for z, but the x1, y1, z2 is already here. So I'll choose z1. And it turns out that this generates the entire Alexander dual of this box polarization. And so you can sort of see how this would generalize. Like if I had a larger up triangle, complete up graph, you can say like, okay, I'm pulling in, you know, an x1 from here, an x2 from here, an x3 from here, an x4 from here, and so on. And then you can build the monomials in the same way. So I'll just say theorem Alexander duals. I'll just say it's not erasing. All my pen stopped working. Okay, it's back. I'll just say vaguely this algorithm gives the Alexander dual for polarizations, for any polarization of powers of the maximal ideal. And then we're able to show using actually even the same sort of visualization that Alexander duals of xyz to the d of polarizations of xyz to the d and x1 xn squared have linear quotients. But this is actually still open in general. And so therefore that means that in these cases, the polarizations are shellable and therefore constructible, and therefore they correspond to topological balls. I just want to say one more thing about Alexander duals. I think I have time to say this and still talk a little bit about Hilbert schemes. So, I have to give a definition before I say this. So we had defined these, so S tilde, right, was built from these variables with the double indices, right? And we put them into these X check sets. One way that you could think about it is you could think about these X check sets as being color classes. And so you could think of a monomial as being color square free, for example, if it only has one variable in each of these color classes, right? So we say that a monomial is a rainbow monomial. Can't spell. Rainbow monomial if it is divisible by one variable in each of the color classes. And you can kind of see from this example up here, I mean, I was pulling exactly one variable from each color class in order to create the Alexander dual of polarizations of the powers of the Maximal ideal. And actually, we show that more generally, the Alexander dual of a polarization of an Artinian monomial ideal, any Artinian monomial ideal, is, I'll say, a rainbow monomial ideal. By that I mean that it's an ideal generated by rainbow monomials, is a rainbow monomial ideal with linear resolution, with, I'll say, n linear resolution, where n, remember, was the number of color classes or the number of variables that you started with. Number of color classes. Okay. And so then the very last thing that I wanted to talk about is I wanted to talk a little bit about connections to the Hilbert scheme. So like I said, the history of polarizations does go back to Hartshorne's proof of connectedness of the Hilbert scheme. And so Lohne had shown that the standard polarization and the box polarization of powers of the maximal ideal, xn to the d, are smooth points on the Hilbert scheme. And so the question is, are all polarizations, and maybe not even just of x1, not even just powers of the maximal ideal, but are all polarizations of perhaps Artinian monomial ideals smooth points on the Hilbert scheme? And this, I mean, an answer to this question would give a lot of insight into the structure of the Hilbert scheme, which has been pretty elusive. And just to give you an idea of how weird it would be if this turns out to be true, is if, you know, so we run some computations, and if you look at the dimensions of the tangent spaces, of poles of just x, y, z to the third, then if you look at the standard polarization, then the dimension of the tangent space there, of tangent space, is, I actually don't have it written here. I think it was 68, it was 69 maybe. And the box polarization gave 108. And then it's bizarre. All the other polarizations give numbers somewhere in between. So if all of these were smooth points, that would mean that they all line up different components of the Hilbert scheme. So it would give a lot of insight into the structure of the Hilbert scheme. And that's actually all I have to say. So thank you.
Cool. Let's use our reaction buttons to thank Ayah. Yay. Questions for Ayah?
I have a question.
Yes.
This nice algorithm you described, does it happen to already be coded into Macaulay?
Sorry, can you say that again? Let me turn up the volume.
So you described this nice algorithm.
Mm-hmm.
Does it happen to already be coded into Macaulay? Can you use this to?
Oh, not yet.
Okay. Well, sounds cool.
Other questions?
Maybe I'll ask a question. So I had a nice talk. Maybe you've seen that there's another way to construct these cellular resolutions for the powers of maximal ideals via these mixed subdivisions. So, basic idea is you think of this dilated simplex as, actually a single simplex added, Minkowski summed up, say, n times.
Mm-hmm.
And then there's this notion of subdividing this thing in terms of the, cells come from basically Minkowski summands of the pieces of the simplices that you, so I don't know, and you can get resolutions of the powers of the maximal ideal that way. I don't know, have you thought about that at all? I just wondering what the connection is to the kind of stuff you're working on here. It's actually a question I've been meaning to ask you for a while, but now that I have you cornered.
I'm not sure.
Okay.
I'm not familiar with that cellular resolution or that construction of a cellular.
Okay. So I might bug you off.
Does it coincide with this one or no?
Well, so the what's called the staircase triangulation, which is kind of one of the canonical versions of this, is the box polarization, as far as I know.
Mm-hmm.
And then, so the natural question is like, do you get all of these kind of polarizations that you have via this, via these different mixed subdivisions? And I'm guessing no, but maybe, when you say just 3 variables, or if you fix it to the square, you might, and so you can actually then control the topology, the shellability stuff pretty well with kind of that picture. So, but maybe, we can talk offline.
Is it a minimal resolution?
So, say again?
Is it a minimal cellular resolution?
Yeah. I mean, in particular, all these mixed subdivisions have the same F vector. So.
Okay, yeah.
And what's nice is actually, these correspond to regular triangulations of a product of simplices. So it's actually, there's like a convexity actually happening as well. So you sort of have space of these things.
Okay.
So we should chat, yeah.
Yeah.
Francesca has a question.
Yeah, thank you. Thank you for a very nice talk. Maybe it's a bit more tangential, but my question is, so the way in which I learn polarization is through the action of the general linear group. You do some kind of general change of variables with some t's, and then the standard polarization is just, the one weight in the t, so, 1, 1, 1. And I was wondering whether you can tell from that perspective, which one of the polarization give you the properties that you want. So maybe there is something about which t weight in the action of general linear group gives you, in that sense, in the old sense of polarization, gives you, the properties that you want, or what is actually, the polarization.
Yeah, so I would have to think about that a little bit more. I mean, I would guess that maybe orbits there correspond to in this picture, like polarizations up to symmetry. But I'm not sure. I'd have to think about it a little bit more.
Yeah, definitely. It just sometimes, you know, it's interesting how the same concept can seem be seen very different from different fields of math, and you know,
Yeah.
the connection could be interesting.
Cool. Other questions? Just great questions, y'all. And great answers.
Hi, Ayah. I really enjoyed the talk. I had to step away for part of it, so maybe you answered this, but I was just wondering, like, if you look at the different polarizations and the multigraded Betti numbers, like, are there some? I mean, it would be interesting to kind of know if there were ideals that you could completely break apart all the Betti numbers, right? You might imagine that the normal graded Betti number is 6, but then when you look at the multigraded one, it splits up into, you know, different components and 6 different ones. And like, for instance, if you just think of the, you know, the ideal like x squared xy y squared, the last Betti number is 2, but really with a standard polarization, those both occur in multi-degree 2, 2. And so is there another polarization where you could break that up? And then an application would be like with like kind of, what is it, consecutive cancellations and things like that. I don't know, this is really interesting to me because I've wondered about these sorts of things.
Yeah, I haven't really thought about that much. I haven't thought much about how to sort of study the resolutions from this perspective. But yeah, I agree that would be really interesting. I'm not sure that in the case of powers of the maximal ideal, it necessarily says anything that interesting, but maybe in the case of other Artinian monomial ideals, it might. Yeah.
Other questions? All right, well, let's thank Ayah again. And 2 reminders. We'll have a tea. Are we calling it tea, Louisa? Right after this for half an hour. And then next week, we'll go back to our Wednesdays at 3 p.m. Eastern time. And Hugh Geller will be the speaker next week from Clemson. So thank you all for coming. And I hope everybody sticks around for tea and socializing.
Thank you, Ayah. Great talk.
Really great.